Hello, my name is Mikolaj Bojańczyk from Warsaw, and in this tutorial I'd like to give you a little bit of an overview of algorithms for logic in computer science, mainly those algorithms which are influenced by automata. The tutorial is going to be organized around two decision problems for logics, satisfiability and model checking. And when I talk about logic in this tutorial, I will mainly mean first-order logic and its variants such as monadic second-order logic, so rather expressive logics with quantifiers. So the first problem is satisfiability. You want to know if you're given a formula and you want to know if the formula is true in some model, perhaps restricted to some class of models. So as I mentioned, I will be mainly caring about the case when phi is of a formula of first-order logic or some richer logics. And here it is not even clear if this is a decidable problem. And as you probably know, in an unrestricted case, it is an undecidable problem. So it might be a little bit embarrassing because this tutorial is partly devoted to the attendance of the SAT semester, and in which case, of course, you are dealing with satisfiability, but this is not the kind of satisfiability that I will study here. So I will study satisfiability for first-order logic and more powerful ones, and not for Boolean propositional formulas. And then the second variant is model checking, where you know both the model and the formula, and you just want to know if the formula is true in the model. The model checking can have several variants, and all of these will be discussed here. So the first one is that in the algorithm, the model M is fixed and the formula phi is the input of the algorithm. This will be most interesting for the case when the model is an infinite model, and therefore it is not even clear how you should why this problem should be decidable. The second case is where both the model and the formula are the input. I will have the least or almost nothing to say about this particular problem. And then the final problem is where you fix the formula and you are given the model M on input, and this will be most interesting if you restrict M to come from some restricted classes of models, such as models which are sparse, and there's been quite a lot of activity about this in the last few years. So there are going to be three parts of the tutorial. The first part, which is now, is going to be about checking the first-order formulas or variants or second-order formulas which are true in a fixed structure. And the second part is going to be about satisfiability, and the third part is going to be about the variant of model checking on restricted classes of models. And as I said, I will not say almost anything about the problem where both the formula and the model are given as input. So let's go straight to part one, and the other two parts you will find in separate presentations. So I will begin with studying which formulas of first-order logic are true in a fixed structure. I assume that you are familiar with the syntax and semantics of first-order logic, and anyway, these are quite natural, so even if you're not, you can even if you do not have a formal education in logic, this should be kind of clear. So these are formulas where you have quantifiers which range over elements of the input structure, and you're allowed to talk about the relations and functions which are defined in the input structure. So the blue example formula here, it says that the relation R is in fact a function, because for every element of the structure X, there exists a Y which is related to it, and in fact this Y is unique because for all other Zs which are related to it, they're equal to Y. And the problem that I would be caring about is, trying to understand which structures or models, I use these words interchangeably, have the following problem being decidable. The structure M is fixed, and you are given a first-order formula of logic without any free variables, so it's a sentence. And such a sentence is either true or false in the model, and the purpose of the algorithm is to decide whether or not it is true. And this is called deciding the first order theory of the model, because the first order theory of a model is just a set of sentences which are true in it. It is also traditionally used to be known as the elementary theory of a model, because elementary logic was just another name for first order logic. Kind of nice name, actually. I don't know why it's fallen out of use. And let's begin with the most simple, non-trivial example. So we want to decide the first order theory of a structure which has two elements, 0 and 1, and it has no other relations or functions on it. The only thing it does have is equality. So our formulas are going to be able to quantify over the elements of the structure, which are 0 or 1. And they will be allowed to compare these elements for equality, and that's all we'll be able to do. So how hard is it to decide if a formula phi is true here? So what can you say with a first-order sentence when you have just access to two elements and you can only compare them for equality? So here's an example of a simple formula. It says that there is some x which is equal to all elements. This formula would only be true in a model which has just one element, and since 0, 1 has two elements, the formula is not true. And in fact, this kind of expressive power is all you need to get p-space completeness. So using these kind of formulas, we will be able to encode quantified Boolean formulas. If you remember, quantified Boolean formulas are formulas where your variables range over values true or false, and once you've quantified over all your variables, you're allowed to write a propositional formula, as in this SAT problem. So you can easily encode a QBF formula in a first-order sentence with equality. The idea is that true will be you guess an element of the formula at the beginning, this red t, and then the true variables are those which are equal to t, and the false variables are those which are not equal to t. So you add one extra variable t, and then replace the proposition in the propositional formula. X, you replace it by x equals 2, and not x, you replace it by x not equals to t. And from this, we can conclude that for every finite model M, not just 0, 1 with equality only, its first order theory is p-space complete. So the decision problem for the fixed structure M of deciding if a given sentence is true is p-space complete. And this is because p-space hardness works already with the simplest model, where you have just two elements and equality only. And on the other hand, membership in p-space for every finite structure is witnessed by the naive algorithm, which just goes for, for every, when you have a quantifier, it just does a for loop which checks all possible values. And then since you need a polynomial, it will in fact logarithmic space to store an individual element, but there might be polynomial in many of them. If the formula is long, then you just run the obvious algorithm and it takes polynomial space. So this is rather simple. So if the model M is finite and fixed, then no matter what it is, at least as long as it's not completely trivial in the sense of having just one element, then its first order theory is p-space complete. So that was a rather easy case. But the problem is interesting not for finite models, but it is interesting for infinite models. So what kind of infinite structures are we going to discuss? Well, the most famous one is going to be arithmetic, and this is a famous structure which is famous for having undecidable first-order theory. But there will also be other structures, and these are the ones that I will be focusing on, where the first-order theory is in fact decidable. And maybe one of the oldest ones is Tarski arithmetic. So this is the real numbers with addition and multiplication. And as it turns out, although superficially it might seem to be more complicated because there's more real numbers than natural numbers, it does in fact turn out that the first order theory of this structure is decidable because they are better behaved than natural numbers. And then another example, which is also has been very influential in computer science applications, is Pressburger arithmetic. So you keep the natural numbers, which are kind of badly behaved with respect to arithmetic, but you keep addition only. There's another example, which is column arithmetic, which is natural numbers with multiplication only and no addition. This is also decidable, but I will not discuss that at the moment. So let's begin with arithmetic. The famous theorem, this was already proved by Church. This is the original undecidable problem. It says that the first order theory of arithmetic is undecidable. This was proved in 1935. And let me just give you a brief proof sketch. I will not go into the details. The idea is that you can use, the central insight is that you can use one number to represent a list of numbers. So the way you do it is if you think of a decomposition of a natural number into its primes, prime factors, then you have a list of numbers there. So it's this the power of the first prime 2, the power of the second prime 3, the power of the third prime 5, and so on. This allows you to represent in a one-to-one way a list of numbers with numbers. And then the main thing is that this representation not only does it exist, but it can be formalized in first order logic. So list operations, such as taking the head of a list, so you input one list and one number which represents a list, and you output another number which represents the first natural number on the corresponding list, or list concatenation, where you input two lists represented as numbers, and you output another list represented as a number, which is their concatenation. All of this can be done in first order logic. So for head, it's kind of easy. You just check the highest power of 2, which divides your input number. For list concatenation, you need to do a little bit of effort, but I will not go into that. But I think you can figure it out if you think about it, unless you haven't seen it, for example, with Gödel's proof. And once you can represent lists and you can do list operations on them in first order logic, then you can just simply formalize the fact that a Turing machine has an accepting computation, because a list can be viewed as a list as a configuration of a machine, and then a list of lists. So a list of configurations is a computation, and then you can write a first order formula which tells you that a list of configurations is a computation. And hence you can write, for every Turing machine, you can write a formula which is true if and only if that Turing machine has an accepting computation. This is it's not exactly how Church proved it, but it is the idea. That how you could prove it now, and hence the first order theory of the natural numbers is undecidable. So there is no algorithm which decides that. Just in case you don't know this, it's amusing to know that it is already undecidable for very simple first order formulas, namely for existential only formulas. And this is because of the famous undecidability result about Hilbert's 10th problem. So if you don't remember, Hilbert's 10th problem can be stated as follows. You are given a polynomial P with integer coefficients and n variables, and you want to know if you can instantiate the variables using natural numbers so that the result, the value of the polynomial is 0. So in other words, does the polynomial have some natural root? You could also have an equivalent statement, which would be where you ask about an integer root, so the xi's would be not necessarily positive integers, and this is equidecidable because every integer can be represented as a difference of two natural numbers, and conversely, every natural numbers can be expressed as a square of as a sum of the squares of 4 integers, and therefore both variants of the problem where you ask for integer or natural roots are equidecidable, and in fact they are both undecidable. So this is a famous result that was proved by Martin Davis, Hilary Putnam, Julia Robinson, and Matiasiewicz. So you can see that this is a special case of existential, because it's just the question itself is just an existential question. Actually, if you think about the proof, it shows even slightly a stronger result, namely that if you take a polynomial and you fix all variables except for one of them, and therefore the non-fixed variables are quantified existentially. So this defines a property of natural numbers, and in fact they show that you can get every recursively enumerable set this way. So for example, because the set of prime numbers is recursively enumerable, it follows that there is a polynomial which is zero exactly on the prime numbers and non-zero otherwise. It's a polynomial with parameters which are existentially quantified. Another funny corollary of this undecidability result, this is a purely generic corollary of any undecidable problem, is as follows. So there is a polynomial such that whether or not this polynomial has a yes answer to Hilbert's 10th problem, so whether or not it has an integer, a natural root, this statement can neither be proved nor disproved using the axioms of, say, Zermelo-Fraenkel set theory with choice, or in fact any formal system. And this is because of a generic result which says that for every undecidable problem you can find an instance of the problem such that whether or not it is a yes or no instance is independent of the axioms. And the reason for that is kind of simple, because if all instances would be dependent, then just searching for proofs in the formal system would be an algorithm. And I think it's kind of a little bit mind-blowing that you can find a polynomial such that you will never establish whether or not it has an integer root or a natural root or not. So now let's move to a structure which does have a decidable first-order theory. And one of the most early and famous examples of such a structure is the real numbers with addition and multiplication, also known as Tarski arithmetic. So Tarski proved, in roughly in the late 20s, but the published version was after the war. He proved that the first-order theory of the field of real numbers is decidable. And the method that he used has been very influential later on, which is called the method of quantifier elimination. So what he showed is that for every first-order formula, possibly with free variables, there exists and can be computed an equivalent formula that does not use any quantifiers. Now, if you want to eliminate quantifiers, you have to be careful about the functions and relations that are given in the logic. So, because, for example, 0 can be defined in terms of addition and multiplication by saying that this is the neutral element of addition, but of course this definition uses quantifiers because it says that for every x plus 0 equals x. And if we care about quantifier-free formulas, then we need to be a little bit more careful. And so we add 0 and 1. We treat addition and multiplication and subtraction, actually, we also added. And we treat all of these as functions, not as relations. So addition is a binary function. And we also have the order. The order is kind of important in Tarski's proof. And because the real numbers are an ordered field, and if you think about the complex numbers, they do not have an order. One can show this, but their first-order theory is also decidable, and in fact also thanks to quantifier elimination. Now, once you have proved that you can eliminate quantifiers, then you get the decidability, because what you do is you take a sentence, you eliminate all of its quantifiers, so you get a sentence which does not have quantifiers. And what can such a sentence be? It can be just a statement which is constructed from 0 and 1 using the field operations, and then these things can be compared for order. And for such a sentence, you can easily decide if it is true. So to illustrate the quantifier elimination phenomenon, consider the following school-like example, where you have a formula phi which has 4 variables. 3 of them are free, so ABC, and the fourth one, x, is bound, and the formula says that there exists a real number x such that ax squared plus bx plus c is equals to 0. So in other words, the ABC represents a quadratic polynomial, and the formula tells you if the quadratic polynomial has a root or not. Now, according to quantifier elimination, this formula is equivalent to some quantifier free one, and in fact it is. You might remember this from your school days. The formula says that b squared minus 4 times ac is greater or equal to 0, and if this is satisfied if and only if the corresponding quadratic polynomial has at least one root. So Tarski's elimination procedure gives you this, so it has to be somehow aware of this. It also has to be aware of this type of phenomenon for not just for quadratic polynomials, but for cubic polynomials and ones of higher degree. And in each case, it gives you a quantifier-free criterion on the coefficients of the polynomial, which guarantee that it has at least one root. And in fact, you can even there's a bit of a funny story here, which is that Tarski, in the time when he was working on these results, to support himself, he was working as a teacher in a girls' secondary school. And so you can imagine that he was teaching things like dividing one polynomial by another, or at least differentiating polynomials. And if you look at his proof of quantifier elimination, then this is actually the kind of things that you do. So maybe he was just bored as a high school teacher, and he just decided to do something with that scientifically, and hence his algorithm. But this is just speculation, and I think it is probably not true. Here's another example application of Tarski's quantifier elimination procedure. If you think about a quantifier-free formula with just one variable x, then what it is a Boolean combination of inequalities of the form some polynomial is greater or equal to 0. And if it's a finite Boolean combination, then since every polynomial changes sign finitely often, then the formula itself will change truth values finitely often, and hence it's going to be a finite union of intervals, closed, open, open, closed, and so on. And in particular, if you think about the property x is a natural number, then this property changes values infinitely often, and therefore it cannot be defined in first order logic just using the field operations. This is not so much of a surprise, because if you would be able to define the fact that a real number is a natural number, then you could also use Tarski's field of real numbers to decide arithmetic, because you would just say, write any formula that you want to text in our arithmetic and just relativize all quantifiers to say that you only care about those variables x which are natural numbers. For similar reasons, you can also not express that a real number is a rational number, and in fact also the field of rational numbers has an undecidable first order theory, because in the field of rational numbers you can actually express that a number is a natural number, and hence use undecidability of arithmetic. On the other hand, the field of complex numbers is decidable, as I mentioned before, because of quantifier elimination. So let me move now to another structure which has the undecidable first order theory, and this is Pressburger arithmetic. So it's somehow incomparable with Tarski arithmetic because it is easier, because it does not have addition and multiplication, but it is harder because it uses the natural numbers instead of the real numbers. So this is a theorem that was proved by Mojżesz Pressburger in 1929, which says that the first order theory of the natural numbers with addition only is decidable. Pressburger's original proof was was presented as a variant of quantifier elimination, because you can show that this structure, the first order theory, admits quantifier elimination if you have a suitable signature. So you expand operations with operations such as a predicate, which tests if something is divisible by 2, 3, and so on. And if you expand your signature enough, then you get quantifier elimination. I will present it, however, in a slightly different way, which is also consistent with Pressburger's original solution, but this is the way that many people think about it now. So what you can show is that for every first order formula, again, we care about formulas also with free variables, so not just sentences which have no free variables. The semantics of the formula, so it's an n-ary relation on natural numbers, is, the lemma says, such a relation is necessarily semi-linear. So what's a semi-linear set of tuples, n tuples of natural numbers? It is a set as in the red writing here. So it's a finite union of linear sets, and each linear set is obtained by taking some basic vector A0, it's an n tuple of natural numbers, and then adding to it anything spanned by some k other n-dimensional vectors. But when you are spanning here, it is your coefficients have to be natural numbers with non-negative numbers. So any such set is called linear, and the final so basis plus a cone spanned by some vectors is called a linear set, and then a finite union of such sets is called semi-linear. So what Pressburger showed is that semi-linear sets are exactly those which can be defined in Pressburger arithmetic. Let's prove that every formula does indeed define a semi-linear set. I will not prove to you the main lemma, but what I will explain is the structure of the proof, because this kind of structure of proof will be visible many times later in this lecture. So it's just an induction on the size of the formula. So let's begin with a basic formula, which is the basic predicate, which says that x1 plus x2 is equals to x3, or it could be x5 plus x7 equals to x2. And if you think about it, the semantics of this formula, so the set of triples such that the first two coordinates add up to the third one, is easily seen to be a semi-linear set. Here, the basis vector is zeros, and it is just any vector which can be obtained by adding a non-negative combination of the vector 1, 0, 1 and 0, 1, 1. So because you can easily see that this spans the vectors which form a legal addition tuple. So this is a semi-linear set. That takes, equality is also a semi-linear set. So the set of pairs such that the first coordinate is equal to the second coordinate is semi-linear. It is spanned by the vector 1, 1. And now you have to show that semi-linear sets have all of the closure properties that you would have for a formula of first-order logic. So you can show that they're closed under union. This is almost by definition, because a semi-linear set is a finite union of linear sets. So you just take two finite unions, you get another finite union. There is projection, which corresponds to existential quantification. I will discuss this in a moment. And then there is complementation. So let's see what do I mean by projection, and what is that? Why is that correspond to existential quantification? So imagine you have a formula with x plus 1 variables. So you have one variable y and then k other variables. So the semantics of this formula is an arity on relation on natural numbers whose arity is x, whose arity is k plus 1. And now if you quantify this variable, if you apply an existential quantifier, then if you think about the corresponding relation, the arity here is k, because the number of free variables is just k. It is the same thing as taking the original k plus 1 array relation and projecting it to the coordinate x1 up to xk, and so erasing coordinate y. So the projection operation, it inputs a k plus 1 tuple and it outputs a k tuple, which is obtained by erasing the first coordinate. And so existential quantification for formulas on the sides of the semantics corresponds to taking a relation of higher arity and projecting the tuples in that relation to some subset of coordinates by eliminating the existentially quantified coordinate. I say this here because the idea that projection and existential quantification are the same thing will appear multiple times later on in this tutorial, and it is good to get used to it in the most basic setup, which is Pressburger arithmetic. So you can rather easily see that semi-linear sets are closed under projection. So all you need to show is that linear sets are closed under projection. And what you do is you just look at all of the vectors and you just eliminate the the coordinate that is being projected away. So that's rather simple. And the only remaining technical thing to do is to prove that semilinear sets are closed under complementation. Now, this can be done using a little bit of modulo arithmetic and greatest common divisors and stuff like that. I don't want to get into the details of this. This would be like 1 or 2 slides because it is going to be a little bit off the central topic here. So I won't discuss this in my tutorial. At any rate, later on in this lecture, we're going to see a complete and alternative decidability proof, which will use automata. So maybe I won't need Pressburger's original proof. These are examples of structures M and the complexity of deciding their first-order theories. So for any finite structure, it's always going to be p-space complete. For the natural numbers and addition and multiplication, also known as arithmetic, the problem is undecidable, but it is decidable for other cases such as Tarski arithmetic or Pressburger arithmetic. I just in the cases of Tarski and Pressburger, I only discussed decidability, but of course there's also computational complexities involved, and Tarski arithmetic is known to be in exponential space, and I believe it is not known yet to be complete for exponential space, while Pressburger arithmetic lies somewhere between non-deterministic doubly exponential time and doubly exponential space. Now, in this tutorial, I will not be giving any more examples of structures with a decidable or undecidable first-order theory, and I will move towards the direction which is more central for my tutorial, which is logics other than first-order logic, and I will begin with second-order logic. So second-order logic is like first-order logic, but you're also allowed to quantify over sets or relations, and also functions, because you can view a function as a set. So let's overview the syntax and semantics of second-order logic. So you can write formulas here. Now you can write special quantifiers, which say you have a quantifier which ranges over elements. This is the usual first-order quantification, but you also have quantifiers which range over, say, binary relations. You have a quantifier which ranges over unary relation, and so on. So for every arity k, you have a quantifier ranges over k-array relations. I used some syntax here with the arity as a little subscript, but I don't think this is the actual syntax that you use for second-order logic. You cannot, however, quantify over third-order objects, such as sets of sets, or relations on sets, or relations on relations. That would only be allowed in third-order logic. But I discuss for the moment second-order logic. So here's a rather straightforward theorem, which says that the complexity of deciding second-order logic is rather easy to understand. Namely, if you have a finite structure, then deciding which fixed finite structure, then deciding which second-order sentences are true in it is a p-space complete problem, while if the structure is infinite, then its second-order theory is undecidable. And this is rather easy to see. Why? Well, if your structure is finite, then p-space hardness is inherited already from first-order logic. And in fact, you don't even need to have a universe which has at least 2 elements, because if you have 1 element in your universe, then you still get to have 2 sets, the empty set and the full set. So it's p-space hard already for structures, every structure with 1 or more elements. Let's say we disallow empty structures. And the problem, while p-space membership still works using the naive algorithm, because how do you check if there exists a relation? Well, you can just loop through all possible relations, and so in order to store a single relation, you just need a polynomial space. So doing a naive for loop across all relations of fixed arity is going to be a p-space algorithm. On the other hand, for infinite structures, you get, no matter how simple your infinite structure be, it could have no relations whatsoever. The problem is still undecidable, because you can just write a formula which embeds arithmetic in it by saying you just guess in the formula a set of triples, which is meant to represent the addition relation in arithmetic. You guess a set of triples, which is meant to represent the multiplication relation, and you say that addition and multiplication are what they should be. So you write out there are some axioms which is particularly in second order logic. And once you have arithmetic available, you can say that your Turing machine holds using the usual undecidability proof for arithmetic. So here I implicitly assume that the structure is countable, but you can carve out a countable subset in second order logic quite easily. So this is true for every structure. Anyway, summing up, second order logic is rather trivial to classify its computation complexity. Hence, we could talk about something else. And it turns out actually that there is some interesting something else. And this is a monadic second order logic, which is actually going to be somehow the main theme of my tutorial. So this is a logic which sits between first order logic and second order logic. And it is the fragment of second order logic where you're not allowed to quantify over binary or ternary relations or relations of arity 4. The only relations that you're allowed to quantify over are unary relations. Hence the name monadic, because monadic relations is the same thing as unary relations. So what I would like to discuss now is try to understand the structures for which their monadic second order theory is decidable. And this turns out to be a place where automata are very important, and hence I am very happy to talk about it. So let's begin with a simple toy example, namely the MSO theory of the simplest possible infinite structure. So you have an infinite universe, the natural numbers, but you have no relations on it, except for equality, which you need to have, at least in this talk. And I claim that here the MSO theory is decidable, and is because of quantifier elimination. So imagine you have a formula of monadic second order logic, which uses this infinite universe and has equality only. So the formula might have some free variables. Some of them might be first order variables, so they describe elements, so natural numbers, and some of them might be monadic second order variables, and therefore they describe sets of natural numbers, possibly infinite sets. Now, if you think a little bit about it, there's not much you can say with equality only, and in fact, one can show that the only things you can say is that an element belongs to a set, and a set has some size, like 5 or 7, or the set has some cofinite size, so it contains all but 3 elements. And these are the only things that you can say, and you can show that these quantifier-free formulas which use these basic formulas, and equality, of course, as well, are the only things that you can express in this logic, and this is proved by induction formula size. So this has a decidable MSO theory. And in particular, if you have an MSO formula which uses all of the free variables are first order variables, then it is equivalent to a quantifier-free formula that uses just equality on these first order variables. Okay, that's not very interesting, but now we'll move to some more exciting examples. So the following question was raised, I think, by Tarski. You can find this quote in a paper by Raphael Robinson, which says that it was Alfred Tarski's idea to discuss an intermediate between first order and second order definition, where you are allowed monadic second order logic. And then the question that was asked is, for monadic second order logic, what happens if you consider the natural numbers with order? And so the paper of Robinson that I'm citing, it showed that, maybe didn't give an answer to Tarski's original question, but it said that it becomes already undecidable with MSO if you are allowed to double numbers. And then he asked, but maybe is doubling necessary or not? And it turned out to be actually a very interesting adventure, which led to many results and a field that is active until today. So what I will begin with in my discussion is a first partial solution to Tarski's question, which is not. We keep the structure of natural numbers with order, but we only care about the weak MSO theory, which I will discuss in a moment. And then, but with the weak MSO theory, it turns out to be interesting in and of itself. And then I will move to a description of the actual solution of Tarski's problem. So what is this weak MSO theory? The idea is that you write formulas which have the same syntax as MSO, so you quantify over elements and you quantify over sets as well, but the semantics of the set quantifier is different. It means finite sets only. So for example, if you write a formula which says that there exists a set which contains all possible elements, all possible natural numbers, then this formula is going to be true in the usual MSO because you can take the set of all natural numbers. But in a weak MSO, it is not going to be true because there is no finite set which contains all natural numbers. So in principle, it seems that the two logics are incomparable. But in fact, over the ordered natural numbers, it is rather easy to see that weak MSO can be embedded in the usual full MSO. In the following way. You can write a formula in the usual MSO where quantification is over all unrestricted sets, which says that a set is finite. Namely, you say that there is a largest, there's a finite there's an element which upper bounds all elements of the set. And therefore, if you want to have weak quantification, you can just simulate it in usual MSO by saying there exists a set which has a finite upper bound. And therefore, for every formula of weak MSO, you can write an equivalent one in full MSO, and hence the problem for full MSO is at least as hard as the one for weak MSO. As it turns out, using non-trivial automata theory, the converse is also true. Over not over general structures, but over the ordered natural numbers, for every formula of full MSO, there exists an equivalent formula of weak MSO. But this is a non-trivial result, and I will not discuss it. Anyway, so what we care about now is deciding weak MSO theory of the natural numbers. And it turns out, this is one of these, the oldest results in automata theory, that the automata theory and logic, extremely influential and seminal result, which says that the weak MSO theory of the natural numbers is decidable. So let me give you a proof of this result, which is going to be using automata. So consider a formula of weak MSO. Now it might have several free variables. In this particular example, it has one first order variable x and two set variables, capital Y and capital Z. Now in Pressburger, when we discussed Pressburger arithmetic, we had some kind of normal form, which in the case of Pressburger arithmetic was semilinear sets, which told us what are the kind of things, kind of sets that you can get from formulas. So we are going to aim for something similar for weak MSO. So we want to describe the relation, the semantics of this formula, which in this particular formula is a set of triples, a number small x, and two finite sets of numbers, capital Y and capital Z. So how do we represent this set of triples? Well, maybe it would be a quantifier-free formula as in Tarski arithmetic. This is what we're not going to do. Maybe some kind of generalization of semilinear set. Well, the answer is we're going to use an automaton. Maybe you could call that a semilinear set if you wish so, but I don't think that would be very well justified. So the big insight here is that we can use an automaton to represent the semantics of a formula. And this is something that we will be discussing many times in this tutorial. So how do you do this? So imagine that you have this triple, which is one number small x and two numbers capital Y and capital Z. Then you can view them as a finite word because you just write for every natural number, is it equal to small x, and is it contained in capital Y and capital Z? So you just write a plus means it's contained in, and minus means it's not contained in. And since your sets are finite, you can just stop at finitely many steps because from some point on, you will in every column you will only see 3 minuses. So you use a finite word, which for every natural number has a column consisting of minuses and pluses, which tells you which sets that natural number belongs to and which of the 3 variables it is equal to. And hence you can represent such finite sets and a number and several finite sets and several finite numbers as a finite word over an alphabet. And in general, the alphabet is plus minus to the power of, well, however many numbers and sets you want to represent. And of course here, if you want your representation to be finite words, it is crucial that you're dealing with finite sets. So once we have fixed finite words as a representation of finite sets and numbers, we can now prove the following, which says that for every formula of weak MSO, if you look at the corresponding finite words, which represent the valuations which make this formula true, these are words over an alphabet plus minus to the power of n plus k, where n is the number of first order variables and k is the number of set variables, then this is actually a regular language. And how do you prove that? Well, it's just a simple induction on formula size. So let's begin with the atomic formulas. So what kind of formulas do you have? Well, one says that first order variable xi belongs to set variable xj. So what kind of language is that? Well, you have to have the words such that in every column, if you see a plus on the column, if in every column, if you see a plus corresponding to xi, then you also see a plus in the column corresponding to xj. So there's just a finite automaton which looks separately at every column and checks if it has this consistency property. It should also check that for every first order variable, there is at most one column which contains a plus in the corresponding row. And again, this can be tested by a finite automaton. The other type of atomic formula is that xi is before xj, and this is just an automaton which checks what? It scans the columns of the word. Each column contains pluses and minuses, and then it checks that if you see the column a letter which has xj a plus on in the position corresponding to variable xj, then you must have seen previously xi or in the same column. Again, this is a finite automaton which roughly just checks that every appearance of some subset of the alphabet is not before appearances of some other subset of the alphabet. So you can write this using a regular expression or an automaton. So we have proved that for the atomic formulas, the corresponding properties of words are definable by automata. And now we can deal with Boolean combinations because of the fact that regular languages defined by automata, are closed under Boolean operations, so union and complementation. On the other hand, if you have a existential quantifier, then the corresponding operation on languages is projection, as we have discussed for Pressburger arithmetic. So the main observation that you need is the following one, which is a rather straightforward observation on regular languages. If you have a regular language over an alphabet where every letter is a pair, and you project away the second coordinate of the pair, then the resulting language is also regular. You should think of the pairs as follows: that the variable that you're projecting, the part that you're projecting away, describes the quantified set. And closure on the projection is rather easy to see for regular languages. One way to view it is regular expressions. If you have a regular expression which describes a set of pairs, then you can just, from the regular expression, you can replace every pair by the corresponding letter. First coordinate, and you have a regular expression which describes the projection. Another approach is to use non-deterministic automata. So non-deterministic automata for the projection uses non-determinism to recognize, to guess the missing part of the word. However, there is a little bit of a mismatch between the type of representations that we use for regular languages to get the different parts of the proof of this lemma. Because if you want to do complementation, then you would like to be working with deterministic automata and not non-deterministic automata or regular expression. On the other hand, as I have discussed for projection, your preferred format would be non-deterministic automata or regular expressions. And in fact, it turns out that this is a problem for the complexity of the algorithm, because if you want to complement, then it turns out that the only way you can really do it is to first determinize and then complement. And therefore, if your formula alternates n times between complementation and projection, then you will need to apply determinization n times, resulting in an n-fold exponential automaton. And by need to, what I mean is that the complexity of the problem is going to be n-fold exponential in the formula size, in the number of alternations that have been described here. So that is the basic idea behind deciding the weak MSO theory of natural numbers. So for a formula we represent, which has free variables, we represent its semantics using an automaton, and then we observe that the automata have all of the closure properties which are required of the logic. And this idea has proved to be incredibly influential, and I will discuss many other instances of it in my tutorial, and this is going to be actually the central topic of my tutorial. But before I do that, let me have some historical remarks. So in the theorem, I gave a number of names, and some of these, if you're familiar with the topic, some of these you might recognize, but maybe some of these you might not. So I will make some historical remarks here. So one of the names is T, which stands for Trachtenbrot, who was at the time in the Soviet Union, and he wrote in published in 1958, but he submitted in 1957 a paper which is called well, here is the Russian name, but it says that it is about the synthesis of logical nets where the operators are defined in terms of formulas that use one-place predicates, so about in terms of monadic second-order logic. So that was in the Soviet Union. And in parallel, Julius Piche and Calvin Elgot in the United States, they also announced the same result in conference proceedings. Later they wrote journal versions, but for some reasons there were two separate journal papers, but the original conference announcement was joined in 1958. And in fact, the conference announcement, the proceedings version is short enough that I can include it here in its full body. So here it is. It can be found in the notices of the AMS, and I have highlighted in blue the main theorem, which, as you can see, it says that the main thing is not the decidability of the theory, but the fact that the sets that you can represent are exactly those that you can define using a finite automata. And it is, I think this is the way that this theorem has been perceived ever since. It's not really the decidability of the theory, but more the insight into the fact that it can only define finite automata describable things. But if you look at the next line below the blue part, you will see here that actually the result itself, so the decidability of weak MSO over natural numbers, so a partial answer to Tarski's question, it actually has been proved before, and it is credited to Andrzej Ehrenfeucht and Vought, and I will discuss this in a moment. So it's a result which has never been published, as far as I know, and which precedes at least Piche and Elgot. I'm not sure about Trachtenbrot, who was working in parallel. So what did Ehrenfeucht and Vought do? Well, it's a nice story. And if you want to have a look at it in more detail, I recommend that you read an article, a column in the Siglog newsletter from 2019 by Wolfgang Thomas. And the story is, roughly speaking, as follows. You can use ordinal numbers to represent numbers and finite sets of numbers. How do you do that? Well, for this particular slide, I assume that you're familiar with a little bit of ordinals. So here's an example of an ordinal. You can write omega to the power of 5. So this is a well-known countable ordinal. The corresponding well-ordered set is 5 tuples of natural numbers ordered lexicographically. And this number omega to the power of 5, you can use it to represent the number 5. And then, but you can combine ordinals together using an operation called ordinal addition. And this way you can represent a finite set of numbers. So, for example, omega to the power of 5 plus omega squared plus 1 is an ordinal. It corresponds to a lexicographically ordered set, and this you can view it as the ordinal, which consists of the number 5, 2, and 0, because 1 is omega to the power of 0. You could also represent some, maybe sets with weights and so on, but this is not going to be used here. So you can view you can represent a finite set of numbers as an ordinal number using ordinal addition. Just if, in case you're not familiar with ordinal addition, you have to be careful, because ordinal addition is not commutative, because if you add ordinals in the wrong way, then the bigger ordinals eat up the smaller ones. So you have to be careful about the order in which you write them. And if you use this representation of finite sets as ordinal numbers, then the basic operations that you want to do on finite sets, such as membership of a number in a finite set, and comparing two numbers for order, and taking Boolean combinations of sets, all of this can be defined using first-order logic, using only the operation of ordinal addition. And you only need relatively small ordinals, ordinals which are smaller than omega to the power of omega, which is roughly the ordinals that I described here. So the ordinal addition applied to finite numbers, finite powers of omega, and their ordinal additions. And Andrzej Ehrenfeucht proved in 1957 that this structure has decidable first-order theory, and then Vaught observed that you can apply these results to get MSO in the way which is roughly described on this slide. And if you want to have a look at the details, as I said, I recommend having a look at the paper by Wolfgang Thomas. So, in fact, the weak MSO application it predates the automata proof, but it is the automata proof that turned out to have lasting value, as you will see in the later parts of my tutorial. But if we continue reading the Piche and Ergot abstract, we read one more interesting thing, which says that the corollary of these results is that Pressburger arithmetic is decidable. This abstract is written in a rather dense style, so I'm not sure what R means here, but Pressburger, I guess it means Pressburger. So I think it's useful to explain how you can deduce Pressburger arithmetic from the results that have been discussed here. So let's have a look at that. So the idea is very simple. If I want to embed Pressburger arithmetic in weak MSO, I just use the obvious representation of a number as its binary expansion. So if I want to represent the number 67, then I use the set 0, 1, 6, which is the powers of 2 that participate in the binary expansion of 67. And if you represent numbers as finite sets via binary expansion, then you can implement in weak MSO addition, because if you just try to think about how you add two numbers, then this can be formalized using weak MSO. You just have to, or a finite automaton, if you prefer that, which reads the two sets with the least significant digit being given at the beginning, and it just the finite automaton just needs to scan the columns and check that everything is correct locally, and maybe needs to have one extra bit of memory for the carry operation. All of this can be easily implemented by a finite automaton and also by a weak MSO formula. So a corollary is that for every formula of Pressburger arithmetic, which is only allowed to use addition, the corresponding n-ary addition relation on numbers viewed as finite sets via binary expansion can be defined in weak MSO, or equivalently can be recognized by finite automaton. So this is an alternative normal form for Pressburger arithmetic, as opposed to semi-linear sets of numbers. We have regular languages of binary representations. So this is an alternative proof for Pressburger arithmetic. This alternative proof, it has the advantage that it allows you to add some stuff to Pressburger arithmetic. Because, for example, suppose that we extend Pressburger arithmetic with an extra predicate which says that a number is a power of 2. This is not expressible in Pressburger arithmetic because the set of powers of 2 is not a semi-linear set. But if you think about numbers which are powers of 2 given in binary expansions, it's easily simply a regular language. It just consists of numbers where there's just, a unique digit is equal to 1. And in fact, you can go a little bit beyond that. You could use a ternary predicate, which says that you are given 2 numbers, y and z, and you say that x is the smallest power of 2 that divides both of them. You can also do this using a finite automaton. You just look at the least significant digit where both y and z have a 1, and x has to be the power of 2, which corresponds to that digit. It's a little bit of an random and arbitrary predicate, but it has the property, actually, that if you add this particular predicate to Pressburger arithmetic, then you get all of the power of finite automata, namely, if you extend it to Pressburger arithmetic with this predicate, the corresponding n-ary relations on, say unary relations on n-ary relations on binary expansions are going to be exactly the regular ones. Maybe it's worth pointing out that some terminology, if you want to look things up later, that the fact that you can take Pressburger arithmetic, let's view it as a group, so it's integers, possibly negative ones. Pressburger's theorem applies to possibly negative integers as well. So then this is an example of an automatic group. So an automatic group, well, there's 2 views on automatic group. One of them is that you can represent, in both cases, you can say that the elements can be represented as strings over a finite alphabet. And then one approach is that the group operation can be implemented by an automaton. And another one, which is actually more popular, is that for every generator of the group, the unary operation of multiplying by that generator can be implemented by an automaton, and groups which can be represented this way are actually a legitimate topic of study in group theory, which was, I think, these observations. There's a book by Epstein and co-authors, and he credits the automata insight in group theory to the great geometer Thurston. But even beyond automatic groups, you can imagine just automatic models, and this is a notion which was based on automatic groups, was introduced by Nerodi and Husseinov. And so what's an automatic structure? It's a structure where the underlying set is a regular language, so some, maybe not necessarily all strings over some finite alphabet, but the strings which are in the underlying set need to be a regular language. And then you want the basic the relations in the structure to be implementable by automata, and then using the proofs, the ideas that you can see on these slides, you can conclude that for every automatic structure, not only are the relations definable by automata as assumed by the definition, but also every first-order formula is definable by an automaton, and therefore, in particular, the first-order theory is going to be decidable. Just an aside about automatic groups, in case you are not confused enough by the terminology, there is also an extra notion called an automaton group, which is also important in group theory. And this is not the same thing as an automatic group. So an automaton group is a group which is obtained by taking some transducers implemented by certain kinds of automata, and as long as these transducers are reversible, then they generate a group, and groups which are obtained this form are called automaton groups, and they have been used to, for example, to provide a counters examples to the Burnside problem. But this is just an aside in case you're interested in such thing. So this completes my discussion of the history and origins of the automata method in logic. So the main players here are going to be Piche, Elgot, and Trachtenbrot, who had the insight that you can represent logical formulas and the sets that they define using automata. And this method has proved to be incredibly influential, and I will give to you some examples of how it has developed later. So the next example is actually about the full solution to the problem raised by Tarski, namely deciding the full theory of MSO over the natural numbers, where you are allowed to quantify over infinite sets. So this was proved by Piche shortly, a few years after the result for weak MSO. So he proved that the full theory of full MSO, where infinite sets are allowed, of the natural numbers with equality is decidable. And it is actually the same proof as for weak MSO, except that now, if you think about a formula with three variables, then in order to describe the infinite sets that are used to instantiate the three variables, you need to have infinite words. So what Piche did is he defined a suitably extended automata to infinite words, and then he developed the necessary automata theory, which was that the language is recognized by these extended automata for omega words, so infinite words are closed under Boolean operations and projection. And this allowed him to prove the MSO theory, the full MSO theory side. So what are these omega automata, so automata over infinite words? Now, I know that there will be a tutorial tomorrow by, the next tutorial by Orna Kupferman about such things, so I will not go into too much detail, but at least I can give you an example. So these are automata which are called non-deterministic Piche automata. And the way it works is that you have the same syntax as for a non-deterministic finite automaton. So you have a set of states. In this particular example, there's two states, a red state and a blue state. And then there's some input, there's some initial states. In this case, the red state is initial, and some accepting states. In this case, the double circle indicates that only the blue state is accepting, but in general, it could be any subset of states. Likewise, initial could be any subset of states. And then you have the transitions of the automaton, and it is non-deterministic because, as you can observe, if you're in the red state and you read a letter A, then you can either stay in the red state or you can go to the blue state. So this is just an NFA, but the semantics are different. So you run a non-deterministic Piche automaton, you run it on an omega word, so on a word with infinitely many letters, where the letters are indexed by natural numbers. I don't know why sometimes people write N and sometimes people write omega, people like myself. I think it's kind of random, at least for me. But for words, you use the word expression omega word. And the semantics are defined as follows. A non-deterministic Piche automaton accepts an omega word if there exists a run, and the runs are defined in the way as for non-deterministic finite automata. But the acceptance criterion is that the accepting state, so in this example, the blue state, appears infinitely often. So if you think about this particular example automaton, if you view it on as an automaton over finite words, it will accept all finite words, because you can have, for every finite word, you can have a run where you just use the red state all the time, and then when you are reading the last letter, you go to the blue state, so that the words have to be non-empty, actually. And then if you view it as a Piche automaton, so you run it over omega words, then if you want to use the blue state infinitely often, you have to use it at least once. So what you do is you read some letters, which are either A or B, and then you non-deterministically at some point decide to go to the blue state, but then you are only allowed to read A letters. So the recognized language is going to be A or B a finite number of times, and then from some point on, you only have A letters, and the corresponding runs will be obtained by staying in the red prefix for some time and then switching to the blue state any moment after the last B has been read. And you don't have to switch when the last B is read. You can even consume some A's if you want to, and then switch to the blue part. Actually, this particular example is a non-deterministic Piche automaton that cannot be determinized, so the corresponding language, so from some point on A's only, this language of omega words cannot be recognized by any deterministic Piche automaton. So it is not a coincidence that I wrote non-deterministic Piche automata, because these are the more important model, and deterministic Piche automata are weak. Now, in his proof, Piche introduced these automata. He didn't use the word automaton. He represented them as some kind of normal form logical formulas, but now people think about them as automata. And he showed, well, although they do not determinize, as I mentioned, but the non-deterministic ones are closed under union and intersection. This is easily shown using a product construction. A projection, this is kind of easy. It's always easy for non-deterministic automata, because if you project a bigger alphabet to a smaller alphabet, and you are given an input word over the smaller alphabet, then you can use a non-determinist to guess the bigger, the corresponding letter of the bigger alphabet and read that. So non-deterministic automata are always going to be easily closed under projection. But the hard part now is, since we are not allowed to have deterministic automata, is to prove that they are closed under complementation. And Piche did show that. This is the principal technical contribution of his paper. And he proved this using the Ramsey theorem. And maybe you might have some more discussion of these topics in Orna's tutorial about automata, so I will not go into that. And this way, Piche proved that the MSO theory of the natural numbers is decidable, but again, very importantly, he did this using the automata method, and the corresponding automata have also been a study as a subject of intense study later on. Now, the next stage is a famous theorem of Michael Rabin, which says that the MSO theory and the corresponding automata method, it works not only for the natural numbers, but it works for the infinite tree. So let me explain what that means. So you can formalize it as follows. So consider the structure where the underlying, it's also an ordered set, but now it is not totally ordered. Now it is, it is, you can think of it as a tree. I will explain why in a moment. And Michael Rabin proved that the MSO theory here is decidable and that there are corresponding automata. So why do I call it the tree, and what is this structure? Well, the elements of this structure are bit strings, and they are ordered by prefix relation. So this can be easily interpreted as a tree. The root of the tree is an empty string. Then it has two children standing for one letter bit strings. And then each bit string can be extended by appending one letter in two possible ways. And hence you have a tree. It's an infinite tree. And the order here is the prefix ordering. Now, you can think about the ordered natural numbers as being a branch in this tree, say the leftmost branch. And you can... for example, so you can embed MSO over natural numbers into MSO over this infinite tree. Here, in order just to save space, I equipped the tree with just the order relation, and there is no such thing as a left child or a right child. Although bit strings do have a left and right child structure, if you think that 0 is to the left of 1. But this is not an important omission, because you can write in an MSO formula, you can guess using existential set quantification a set of vertices which are called left children, and then verify that you have correctly checked by saying that for every node there exists one child which is a left child from your guessed set, and one child which is not in the set, and then use this set as your notion of left child. It will not necessarily coincide with 0 and 1, but that's not important. Anyway, so this is the structure of the tree, the infinite tree. I would call it the Rabin tree of it has a root, and then every node has two children, and it is ordered by the prefix root. And what Rabin proved is that the MSO theory of this structure is also decidable. Rabin's proof did use automata, using a notion called Rabin tree automata, but I will describe to you a similar and more commonly now used notion called parity automata. I will not give the proof because it is rather complex, but I will at least say what are the main ingredients. So the kind of automaton that is used is called a non-deterministic parity tree automaton. And how does it work? Well, first of all, I have to tell you what a tree automaton is. So a tree automaton it works as follows. If you have a word automaton, then a transition, it looks as follows. You have an input letter, you have the state before you read it, and you have the state after you read it. So a tree automata is the natural generalization where you imagine that you start the automaton in the root, and then you have the state P before you read the letter, and then once you read the letter, you branch into the state in the left child and the state in the right child. So a transition, instead of being a pair of states and an input letter, it is a triple of states and an input letter. And I will be caring mainly about non-deterministic automata here. If they're deterministic, then there are several variants of deterministic ones, such as is it deterministic bottom-up or top-down, but I will not discuss this right now. And what is the parity condition? Well, this is, it turns out that if you take a non-deterministic tree automata with a Piche condition, so we have an accepting set of states, then that is not going to be expressive enough to cover MSO, but there is a generalization called parity, which does the job. And it works as follows. So in the automaton, instead of having an accepting set of states, and the requirement then being that you see an accepting state infinitely often, you have a more complicated acceptance condition. And in the parity condition, it's called it's given by a parity ranking function, which assigns to each state a number. And then a run is considered accepting. Well, in a tree automaton, it's considered accepting if for every branch of the tree, so like every sequence of nodes obtained by starting in a root and taking a child, so that's a branch. So for every branch in the tree, if you look at the maximal rank that appears infinitely often, then it has to be accepting, and accepting here means an even rank. So 0 good, 1 bad, 2 good, 3 bad, and so on. So the first time you see a parity condition, it might strike you as a bit artificial, but it turns out to have central importance in the theory of automata over infinite objects, as you will find out later on during the tutorials of this bootcamp. So that's a non-deterministic parity tree automaton, and you use it to recognize a property of infinite trees, where an infinite tree it's a Raven tree with nodes labeled by some finite alphabet. So in other words, a function from 0, 1 star to the finite alphabet. And using standard automata constructions, you can show that languages of infinite trees, which are recognized by parity tree automata, are closed under union, intersection, and projection. Well, if you have to deal with the parity construction, it's a little bit there's a little bit of a challenge for, say, intersection, but you can deal with it. Projection is the usual non-deterministic thing, and union is even simpler, because if you have two automata, you can just write them side by side, and then the recognized language is going to be union. However, complementation is problematic. And the main technical content of Rabin's paper was a proof that, non-deterministic tree automata, in his case, it was not with the parity condition, but with the Rabin condition. But that is very similar, that they're closed under complement. And this is the main part of Rabin's theorem. And the way you would probably prove it nowadays is you would go, not to deterministic automata, because unfortunately there's no known, and it doesn't seem to be possible to have a good deterministic model for tree automata, but you use a different model called alternating parity tree automata, and these are defined well. If you're familiar with alternating automata, you can sort of guess what they will be. And these have the nice, they're trivially closed under Boolean operations, especially complementation. And then the main technical work is to show that the two models are equivalent. And non-deterministic is a special case of alternating, but the main content of Rabin's theorem is to prove that you can de-alternate parity tree automata, and this is something that uses two important automata results. One which is that automata and omega words can be determinized, not using the Piche condition as I mentioned before, but using if you use the parity condition, it works. And then the second important thing is there's a game aspect to it, which will be discussed, I guess, in the tutorial by Marcin. So if you put all of these ingredients together, it's a highly non-trivial result. Then you get Rabin's theorem that these regular languages, these automata, since they're equivalent, they have all the closure properties of MSO, and hence you can compute for every MSO formula with free variables an automaton which recognizes the corresponding language and thus decide the theory. And this is a very powerful result which can be used to obtain, it generalizes all of the previous ones, and it can be used to obtain many decidability results. And I guess that you might find out more about how this is actually done in Orma's talk. And now let me move to the last example of a structure with decidable or not decidable MSO theory. And this, in fact, is going to be a negative example. So it shows like where problems start to appear. This is a remarkable theorem, which says that if you take the ordered real numbers, so you generalize from the ordered natural numbers to the real numbers, then you get an undecidable MSO theory. Now, this I think is kind of strange. So, for example, if you think about first order theories, not MSO theories, then the real numbers and the rational numbers have the same satisfy the same first order formulas or well sentences. It's easy to see. You can play an Ehrenfeucht-Price game between the two, but this does not extend to MSO theories. And in fact, for example, the basic property, defining almost properties of the real numbers, such as saying that every set has a least upper bound. This is an MSO sentence, which is true in the real numbers, but not true in the rational numbers. So there seems to be something going on, but you would think that maybe it's not such a big difference, but in fact it's a huge difference. So it's a result that was proved originally by Schelach in 1975, that the MSO theory of the real numbers with order is undecidable. His original proof assumed the continuum hypothesis, but later on in the 1980s, in work together with Yuri Gurevich, it was shown that the continuum hypothesis is not necessary to prove this result. And this is a very difficult proof. I will not even present the main ideas in it. What Schelach manages to do is to encode numbers and addition inside real numbers, inside sets of real numbers, and the only available structure is the order. Now, this is a bit strange because there's not much you would, if you try to extract any arithmetic from the real numbers in order, it would be very hard to do. So here is at least a witness of why it should be hard. So consider an MSO formula over the real numbers with order. We have just one free variable that's first order. What properties of a real number can you express? Well, actually, really nothing. You can just say true or false. And the reason is very simple, because suppose you have a formula of MSO which is true for x equals 5. Then I claim it's going to be true for every other x. And why is that? Because you can map the number 5 to any other real number using any order-preserving bijection of the real numbers. And since there's every number can map to another one using an order-preserving bijection, and order-preserving bijection, also known as automorphisms of the structure, will preserve the truth value of a first-order formula. It turns out that if your formula is true for 5, then it's also true for 7, pi, I, or whatever other number. So whatever proof you're going to have, such as Schelach did, then it's going to have to be invariant under such automorphism, and as I just mentioned, they can take any number to any other number. But these automorphisms really kill first-order logic, but if you go to monadic second-order logic, they do not kill it anymore, although why it's not so easy to see, and the proof, as I said, is complicated. A second counterpoint is that the MSO theory of the rational numbers with order is decidable, and it is maybe nice to see this as an application of Rabin's theorem, because if you think about the Rabin tree, you can view it as natural numbers. Why? Rational numbers. Why? Well, you can just order the nodes of the Rabin tree by just appear to the left on the picture. So what does that mean? That means that if you have a node of Rabin's tree, then all of the elements of its left subtree are before it, and all of its elements of its right subtree are after it. And if you consider the order defined this way, then you will easily see that it's a dense ordering, it's countable, and it doesn't have any endpoints. And it is well known that if you take any order which is dense, countable, and has no endpoint, then it is isomorphic to the rational numbers. So this way, you get the rational numbers inside the Rabin's tree, and you can use Rabin's theorem to decide it. This particular construction uses the notion of left and right, but as I mentioned before in my tutorial, you can encode the notion of left and right by just guessing an extra set in Rabin's theorem, in the Rabin tree, which represents the left children. So this way, we can see that using Rabin's theorem, we can decide the MSO theory of the rational numbers. There is an alternative method which does not go through Rabin's theorem and was actually originally proposed in Schellach's paper and later developed by Carton, Colcombe, and Puppis using semigroups for rational numbers, but instead of automata. But I will not go into that. In fact, it's an interesting case because there is, as far as I know, there's no known notion of automata for rational numbers. So the existing methods need to avoid this either by going into a richer structure of trees where you do have automata, or by developing semigroup methods over the rational numbers themselves. So this theorem shows what are the limits of the automata method. So for example, for the ordered real numbers, the MSO theory is undecidable. And this brings me to the conclusion of the first part of my tutorial, where I gave you examples of structures where the first order theory or the monadic second order theory were decidable. And my main focus was to choose structures so that the decidability of the theory would follow from a translation of formulas into equivalent automata. And now, in the later second and third parts of my talk, I will discuss applications of these methods and others to the satisfiability problem, and also to the variant of the model checking problem where the formula is fixed. Thank you.